I'd just like to thank the organizers for allowing me to speak here. It's always a pleasure to be here in Santa Cruz. It's been a lot of years here, and it's always good to be back. It's a very beautiful place, and I enjoy it quite a bit. So what I'm going to be talking to you today is about what we can learn about the buildup and evolution of galaxies in the first few billion years of the universe. And there's thanks to many of my collaborators for making a lot of this work possible. Before getting on to the meat of my talk, I think it's very amazing to step back and think about what amazing progress we've made over the last few years in studying galaxies at very early times. That's really due to lots of very state-of-the-art instrumentation on HST, Spitzer, and a lot of other ground-based observatories. WITH-3 has been particularly useful, basically completely expanding the discovery potential of HST toward the high redshift universe, increasing by a factor of 40. Many of you may remember when Nick Mouse was taking data. Here's a little image of the Hubble ultra-deep field. This is effectively 144 orbits. And let's see, do we have a... Okay, this is 144 orbits. This is what you get with WITH-3 with slightly more orbits, but the contrast is pretty profound. Here are essentially we only knew 4 redshift 7 objects in this field before WITH-3, and here were some of the faintest ones. As you can see, the signal to noise improves pretty profoundly, and so there's been enormous progress before WITH-3, after WITH-3 over the same field. Basically, including all fields, gone from a situation where you have about 15 to basically on order of more than 800, redshift greater than 6.5 objects. So why are studies of galaxies at very early times interesting? There's many reasons. It's when galaxies are first forming. The halos of these objects are forming over this time period, so the evolution is pretty profound. It's also when the universe was reionized, and so it's interesting to investigate whether galaxies can have anything to do with that. I'm going to be focusing this presentation on the galaxy growth from redshift 10 to redshift 4. So there's different regimes to study galaxy growth. One can try to study the growth of very faint galaxies with sort of more normal objects, where most of the stars in the universe form. If you're studying the normal faint galaxies, those are pretty important to study, and there's several important questions you could ask and try to answer. One of the questions you could try to answer is how rapidly do the low mass stars do these galaxies build up, and you can basically answer these questions with things like the Hubble ultra-deep field and similar fields. So that's obviously one regime you can study galaxy growth. The other regime you can try to study galaxy growth is not looking at the faint galaxies where most of the stars in the universe form, but looking at the bright galaxies. And there's a number of important questions you could try to answer regarding their growth. You could try to understand, basically how fast they grow again, what is the rate of evolution. You can also try to answer the question, how bright or massive can galaxies become? Is there a maximum brightness? Is there some point that various things like feedback or dust extinction start to limit things? And this you can answer using very wide area fields. So I'm going to be focusing most of my presentation on what one can learn about galaxy growth from the very wide area fields. There's been a lot of work done on galaxy growth over the very faintest surveys. I'm going to be talking more about the wide area surveys. And so many of you obviously are very familiar with many of the different data sets that are ideal to try to answer these types of questions. So in terms of the ultimate wide area survey with HST, it's really the full candles program. There's also data sets like Borg or the ERS field, which are also useful. Anyway, this full candles program really provides the ideal data set to really probe the properties of the most luminous, the brightest galaxies. Here's a nice visual that I've stolen from one of Harry Ferguson's presentations on the web. And you really like to use all five fields. Why is it useful to use things like the full candles program or very, very wide area fields? Well, again, here's a plot of the total numbers of redshift 7 objects as a function of UV luminosity. If you look at the deepest fields, you see that these things are predominantly very faint. There's not many numbers at the bright end. However, once you start folding in the wider area fields over candles, and these are 2 of the candles fields, and these are the other 3, you can basically really start filling in and getting substantial numbers at the bright end, really allowing us to learn things about what the brightest, most massive sources are like, as our maximum luminosity, what else can we learn, what is their dust extinction, what are the things about these things. And basically, you can even learn more if you extend over wider areas from ground-based data like UDS or UltraVista. Another thing that's useful about having a program like Candles is that it allows us to essentially overcome field-to-field variance. One big concern is large-scale structure, and so one might be concerned that if one looks at a certain part of the sky, one may not be looking at an average region of the sky, and large-scale structure may cause a problem. And this just shows you the relative normalization of the luminosity function that we derive based upon analysis of all here of 5 candles fields plus the Borg-Kippis program. And this shows you that basically suggests that as you go to higher redshift, the field-to-field variance may be a little bit larger, and this can be particularly concerned at the bright end. And so there's lots of great data sets, and so what can we learn about galaxy growth? So I'll be trying to look at this with the luminosity function, the high redshift luminosity functions. You could also try to take a step further and look at mass functions. However, luminosity functions are really the closest to the data, and you require less assumptions to derive them. And so we've tried to do we put together a fairly comprehensive paper on very luminosity functions. Here shows you various data sets that one could look at and trying to derive luminosity functions. Here are these various redshifts. We could derive them. Here are some of the more well-known state-of-the-art studies at the time. We were trying to update this substantially by essentially updating the entire thing at one time. We'll also be trying to update the frontier fields. We put a paper out. We're currently working on a revision of this paper to essentially try to do as much of this as possible. One significant question, which has been the debate amongst people who are working on this, is it possible to use the whole candles area to do this? If you have the candles north and south, you actually have HST coverage over the full range of wavelengths to sort of do the selection. Basically, if you have if you have sensitivity to all these different wavelengths, you can very sensitively look for a Lyman break. Lyman break is this, indicates where the likely redshift of a source. And so if you have sensitivity at all wavelengths, you can obviously select very distant objects very well. If you actually look at over the other candles fields, the HST coverage is a little bit more limited. And so in essence, and in particular, there can be gaps in the HST coverage. Fortunately, you can try to make up for this by taking advantage of ground-based data, and the ground-based data largely can fill in a lot of the gaps. And in particular, there's some Y-band data over at least 2 of the fields, and they go pretty deep to around 20, basically pretty deep, 27th magnitude or so. And so you can largely deal with this. However, we admit that some regions of this parameter space are a little more challenging to fill in. And so this effectively can give us a luminosity function from redshift 10 down to redshift 4. And as you look, just looking at redshift 10, 8, 7, 6, 5, 4, you basically see there's pretty evidence of galaxy growth. However, we can try to address more specific questions in this. A few other highlights. Based upon current programs, you can select large numbers of objects. Of over like 10,000, 11,000 objects over, essentially all the wide field, the UDF and things like the Candles program. You can also, there was they'll advertise. Well, yeah, this paper along with Ushal derived the first redshift 10 luminosity functions. Anyway, so what kind of questions can we answer with these data sets? One question you could try to answer is how bright can galaxies become? I said how bright or massive can galaxies become? And amazingly, what the answer we found by looking at the Goods North data or the Candles North data is that they can apparently become very bright. A lot of the objects that we found over the goods north were 10 to 20 times brighter than the redshift 9 to 10 candidates in the Hubble Ultra Deep Field. Some of the best redshift 10 candidates, in fact, are as bright as L-star galaxies found at redshift 3 by Steidel. And these were all reported on in this very nice paper by Pascal Usch in 2014. And this just shows you one of the objects. This is one of 6 bright objects. Basically, object shows up at over 10 sigma significance in the H band. It's detected with Spitzer at more than 6 or 7 sigma. It's detected at a few sigma in the K band. And basically, you get this is the SED that you get for this candidate. And you can see it looks to be fairly robust. Basically, completely flat SED here, very sharp Lyman break, and the optical limits are very, very tight. And in fact, the difference in delta chi squared is basically 40. So it's pretty significant. There's another 5 candidates that are available. This just shows you what you get. Tight optical limits detected with Spitzer. Flat spectrum, redward of the break. And so basically, again, here's a redshift 9.3 candidate. This is what it looks like. It's not, basically here you can detect it at basically 5 sigma in at least one of these bands, in this band for sure. This detected about probably 8 sigma. So again, 6 bright objects over the candles north and south. And so this was an amazing thing to discover, since we didn't know if these objects existed. However, these sources are quite rare, and so they can take quite a bit of effort to find. So you might ask, well, should we believe these objects? The images I showed you weren't spectacular. So it turns out that they seem pretty believable. If you do estimate the formal probability of contamination, it's pretty low. Here is this black histogram, shows you the contamination probability for an HUDF XDF sample from Ellis and Usch, roughly 5%. It's pretty low. But if you actually look at this bright candle sample, the contamination probability is 100 times lower, basically because you can detect it with Spitzer and you can get such tight optical limits on the optical flux from HST. What else? Should we believe this? Well, you can actually look at the volume density of these sources, compare with predictions. You can take the luminosity functions at redshift 4, 5, 6, 7, and then use a simple halo growth model to extrapolate to redshift 10. And this is what you get for this nice simple extrapolation. This is what you get if you actually take Pascal sample and you basically derive a luminosity function. You can see it pretty much agrees pretty well. So it seems that it passes this test. It seems plausible from this test. What about the sizes? Do the sizes of these candidates make sense? Well, you can actually take lower redshift, very bright galaxies and measure their sizes, and then just extrapolate this to redshift 10. And this is the extrapolation, and this red point shows you the average size that we derive from HST data, and it perfectly agrees with the extrapolation. If you would actually compare with the interlopers for this sort of selection, they would be up here. And so you can see that basically these things perfectly match the predictions, and they completely different than the contaminants. What about the colors? This shows you the colors of these. Let's see, this shows you the colors of a similar luminosity redshift 5 sample. This is blue, this is red. This is a number of the sources. The bright redshift 9 to 10 candidates are all fairly blue, and actually bluer than an equivalent redshift 5 selection. And so again, they basically have all the properties you'd expect for being at very high redshifts. So how do these candidates compare with the most distant galaxies ever discovered? Here's my own informal compilation of the highest redshift objects before Usch et al. 2014. You can see the discoverer, the redshift, and some name for the object. And you can see on here, if you look at this list, various CLASH candidates, lens candidates from the CLASH program, sources from the HUF-12 program, and sources. And there's actually one source that we identified in our original Nature paper, which is actually this one right here, which looks to be seems to be, well, not 100% robust, but pretty robust. So now, if we add the Usch et al. Candidates, what does this look like? If you do this, you actually can see that we're actually doing pretty well with this candle sample. And so we effectively have 3 of the 4 most distant galaxies known, basically by looking at the goods north, the candles north and candles south. So what science can we expect in cycle 22? Well, fortunately, things went pretty well in the cycle 2. In the proposal review, we had a proposal approved to essentially follow up one of the brightest redshift 10 candidate over candles north with GRISM spectroscopy. And so the idea will be get spectroscopic confirmation of a redshift 10.2 object through a continuum break. This could potentially kill this whole idea of searching for the most distant galaxy ever, or along with a Coadal object. If we can get a spectroscopic redshift around above 10, I don't think people will be trying to look for the highest redshift object with Lyman alpha anymore. We also had a proposal approved to essentially, we pre-select, we look for, throughout the entire candles program, there's 3 other candles fields that we didn't search so far, and we look for the most promising redshift 9 to 10 candidates, and we essentially got, follow-up data, we got follow-up imaging data on all these candidates. We got 11 orbit program, and we estimate conservatively we should be able to find roughly 7 more redshift 9 to 10 objects with this program. This was approved, and this is just an example of the SED. Won't go on, but it looks pretty convincing already, even without the follow-up data. But the new data will test its nature even further. Basically, and there's also this very big program, pure parallel program with Michele-Trente, basically looking at lots of random points, sight lines, to try to find large numbers. It's basically a 500 orbit program to look for more redshift 9 to 10 objects. So basically, likely 15 more bright redshift 9 to 10 objects from more than 500 orbits in the next cycle. One can also play the same game at redshift 4 to 8 and say, how bright can galaxies get? We ask this question at redshift 9 to 10. We can also ask it at redshift 4 to 8. Now, it turns out that things seem to get pretty bright if you use the full candles fields. Called candles area, you can find very bright objects. You can try to approximately quantify this using a Schechter fit. And again, this is best derived using as many candles fields as possible. This maximum UV luminosity is similar to a characteristic luminosity, and it appears to evolve relatively little out to redshift 7, and then may evolve more out to redshift 8. Okay, so many of you have heard me say that basically galaxies are building up, and they continually get brighter with cosmic time. And so you may ask, how does this agree with this idea that maybe the characteristic luminosity doesn't evolve as much? I've heard me say things like, basically, galaxies are merging and they're getting bigger and bigger. And we had this paper where we tried to approximately quantify this upsizing of galaxies and UV luminosity. Now, it turns out that we still think this is going on for normal galaxies. You still have the same sort of evolution. And basically, you can actually quantify this better using a cumulative number density matching formalism, which comes up with exactly the same answer. And if you actually look at this, so if you actually use a sort of luminosity evolution scenario, you still get that answer, but only for normal galaxies. So this is the evolution of UV luminosity for a normal galaxy based upon our 2008 scenario. Based upon 2014, we basically get exactly the same answer, modulo slight shift, but basically get the same answer. So basically, this whole idea that galaxies normal galaxies are continually getting brighter in terms of their UV luminosity with cosmic time is still true. That basically galaxies, just start out small, they get brighter and brighter and brighter. You might ask, well, maybe we'd expect the same situation for even brighter galaxies. Maybe you have a bright galaxy and it keeps on getting bigger with cosmic time. Well, it turns out that eventually this doesn't occur. Basically, there's a maximum UV luminosity at some point where things don't get any brighter. And so basically, you have a situation where if you look at the brightest possible luminosity, maybe things start getting brighter and then they meet some maximum. So why would galaxies reach some maximum luminosity if they're growing? If galaxies are growing with cosmic time, why would they reach some maximum UV luminosity? And it's a very simple explanation that UV luminosity is not a physical parameter. It's not like, well, it is a physical parameter, but it's not, it doesn't deal with the underlying physics of a galaxy. Things like the star formation rate are effectively something more fundamental. And so what can happen is you can have a galaxy that starts out small and gets bigger and bigger and bigger, and have its star formation rate get brighter and brighter and brighter, and eventually at some point you will eventually, due to dust extinction, basically have the UV luminosity saturate. So basically you can have a galaxy which is, effectively the star formation rate is increasing with time as, essentially the dark matter halo and the accreted gas is getting more and more, and then eventually you can imagine that it will effectively saturate at some value. And this idea, well, there was basically this whole idea that UV luminosity could be set, L star could be set by dust extinction, was actually first proposed in several papers here. This is a plot from Bouwens et al. You don't have to follow this, but basically, as the bolometric luminosity increases, the UV luminosity doesn't follow suit and it saturates. So we can put together a very simple model for the evolution of the luminosity function just based upon a dark matter halo, assuming that the light trace is mass and the light trace is effectively the halo mass. And so you can just basically put together a simple model. You're just basically taking the luminosity and you're taking the mass of the dark matter halo and converting to luminosity. And then you just assume that the UV luminosity saturates at some saturation luminosity. And so you end up with something like this. This is basically just halo mass evolution. And you can imagine that eventually things saturate due to the fact that dust extinction kicks in and stops things from getting brighter. And so if you were trying to parameterize this evolution, you may initially have luminosity evolution, and finally you get some density evolution coming into the mix as effectively you hit the saturation luminosity. What about you could also do the same game with the bolometric luminosity function. So instead of UV luminosity here, you could put bolometric luminosity. And if you do this, then dust extinction isn't so important. And effectively, you can have something like you basically just have the evolution of the halo mass function. And so you could just maybe have something which seems more keen to luminosity evolution. Of course, you could imagine quenching eventually could become important at some halo mass. So, how long? Okay, 4 minutes. Okay, so one quick thing. Could dust extinction? Let's see. I'm trying to think. I should skip past this. So one question we could try to ask is, we could try to answer is whether dust extinction sets an upper limit on the UV luminosity of sources. And so one way of potentially investigating this is to plot the colors of objects versus their luminosity. And this is a plot at redshift 4. Basically, these blue circles show you the mean value. These are from all of essentially candles north and south. This is from the ultra-deep fields. And basically what you see is that basically the brightest objects tend to be the reddest, and the faintest objects tend to be the bluest. And what you notice is that the dependence appears to be slightly steeper maybe at the bright end than at the faint end. And well, it seems to be obvious from this, but it's only significant at about 95% confidence. This is flatter and a bit steeper here. And so that if you have a steeper dependence at brighter magnitudes, you might think that some process is essentially causing things to start getting much redder as things get more massive. And maybe it's dust, maybe it's age, but this is just effectively UV. This is the color of objects versus their luminosity, and this is approximately equal to the mass, at least before you get to the brightest objects. So you see this trend, and you might not believe this trend in the UV, but if you can also plot the same trend as a function of this is the rest frame optical luminosity. So I've showed you before, this is the UV luminosity, this is rest frame optical. Again, you see this sort of tendency for things to be a bit flatter at the faint end and to really start moving at the bright end, which is suggesting that some physical process is really starting to change their color. And if that's dust, you could imagine that as you're getting to very, very high luminosities that maybe dust extinction is effectively causing things to cut off. And if you can actually look at the same trend at other redshifts. Here's redshift 4, which I just showed you. You can also look at this beta versus UV luminosity at redshift 5 and redshift 6. You see somewhat similar trends, which suggests that something like this could be going on. And you can actually effectively plot the beta versus luminosity relationship for all redshifts effectively on the same plot. This is, again, this is fairly similar to mass. And basically what you see is effectively somewhat of a steeper dependence at the bright end than the faint end. And if you actually look at redshift 4 systems, the dusty high star formation systems generally lie here. And so this is kind of a hand-wavy argument, but basically the fact that you start having dust extinction, maybe some processes like dust extinction start having an important effect on the colors at the bright end, and it consistently at all redshifts suggests that maybe something could be going on to essentially attenuate or make things fainter, basically to cause the UV luminosity to saturate at the bright end. And so anyway, I won't go on to that. One other thing I just wanted to quickly touch on, and then I'll finish the talk, Jennifer, so don't worry. So I've talked about many of the other changes. I've talked about how the brightest possible source at each redshift. I've talked a little bit about how that evolves with cosmic time. Another thing that one can look at is the faint end slope, and how does the faint end slope change with redshift. And so we've actually gone out and tried to determine the faint end slope all the way between redshift 4 and redshift 8. And these are our constraints, these red points. This gray curve shows you essentially the 1 sigma contours for the evolution. And as you can see, there's fairly significant evidence for evolution of the faint end slope with redshift. Previously, there was such evidence presented in some of my work and other works, but previously it was only significant at 2 sigma. Now it's significant at basically 4.5 sigma. What's interesting about this evolution is it's almost exactly what you'd expect from the evolution of the halo mass function. If you look at the steepening of the halo mass function, you find almost exactly the same evolution. And so basically, if you just run this movie, this is the movie where you essentially you just take mass and convert it into light, mass and convert it into light. But you can see that the effective slope of this luminosity function is changing with cosmic time. And that is just due to the evolution of the mass function. And what we find for the luminosity function is exactly the same evolution. We find exactly the same going from a very steep luminosity function, steep faint end slope to a shallow faint end slope. You can actually look at this in a parameter-free independent way. If you effectively take all the luminosity functions and you effectively slide them vertically, you essentially adjust their normalization so that they all match here. So you just take the luminosity functions I showed before and then just slide them to force them to fit here. If you slide them to force them to fit here, you basically find this very nice trend from redshift 4, 5, 6, 7, and 8, where you basically just see the luminosity function just steepening up. And this steepening that we observe is very, very close to what you would expect from almost a naive model for the evolution of the halo mass function. So I'll just skip all this and just jump to the conclusions, because I'm probably way out of time. So anyway, in terms of a few summary points, based upon current surveys, we can identify large numbers of very, very high redshift objects, and as much as 15 objects already at redshift 9 to 10. We found some very, very bright and luminous galaxies at redshift 9 to 10 over the CANDLES programs, and they have all the properties we would expect. If there were redshift 9 to 10 objects based upon very simple-minded predictions. Basically, these bright objects over the CANDLES field appear to be even more robust than the faint objects in the UDF. And we expect to find more of these bright objects based upon ongoing surveys. basically using the large sample of very bright redshift 4 to 7 galaxies from candles and other HST programs like Borg, we can really set robust constraints on the number of bright sources. Effectively, the maximum luminosity or characteristic luminosity doesn't seem to evolve that much between redshift 7 and redshift 4. We think this is likely due to the fact that the UV luminosity of sources is saturating due to dust extinction. That effectively, once you get to a certain star formation, dust extinction starts to be so important that things don't get any brighter. And we observe very strong evidence for a steepening of the Feynman slope from redshift 4 to 7. So thanks. Yeah, that is correct. That's correct. It was intentionally too simple-minded.
Whereas quenching will, of course, take the objects out of the diagram completely. So my question is, if you say it's quenching, what is the characteristic stellar mass which you obtain by taking the characteristic star formation rate, applying the SSFR of the main sequence to derive a stellar mass?
I think I would have to do this calculation properly, but I think it's around 10 to the 10. It would be around 10 to the 10 solar masses. Now, this is something we'd have to talk about afterwards, and to discuss in detail afterwards. But my personal belief, and again, it would take some time to justify this, is that basically the cutoff is being set by dust extinction rather than quenching. I think quenching will eventually become important at some mass, but my feeling is that that most of the reason for the cutoff that we observe in the UV luminosity function at high redshift is due to dust extinction. But that's something that we could debate.
And not even the halo mass function, because that's going to become much more important.
Yeah, well, eventually, once you get to high enough redshifts, I think that starts to become important. But the cutoff in the halo mass function at redshift 4 to 6, if you actually take everything and scale it, would tend to be brighter than L star. If you would just take mass and convert to light. But this is things we could talk about afterwards.
Okay, question for Joel, and then I think we'll move on.
So again, on this issue of what causes the inherent saturation of the UV luminosity, if it's true that the dust is absorbing the energy, it must be re-emitted at longer wavelengths. And since you showed a plot that showed that there's something similar going on in many different redshifts, including down to lower redshifts, it should be possible to verify this with data from Mr. and Herschel. Try to do that?
Well, we're going to work on it, but it can take some work to do it.
Well, the truth is that the Herschel images are going to be confused.
I realize that takes a lot of effort. I mean, obviously, if one had infinite amounts of ALMA time, one could do this very, 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 very well indeed. But it's something we want to work on, but it could take some effort.
I think
mention
it's
the
a
argument,
really
so
question
that's
James
an obvious
will
approach.
answer.
Yeah. It'll just take some effort. I mean, we can only work on so many papers
Let's thank Richard again.
at a time.